What specific problem does the proposed method aim to solve?
The proposed method aims to solve the issue of passive exploration in online alignment frameworks, where standard methods suffer from overfitting and premature convergence, leading to responses clustered around local optima. This passive exploration mechanism can leave potentially high-reward regions unexplored, hindering the development of more capable language models. The method addresses this problem by introducing an active exploration approach that elicits novel favorable responses through an optimism term added to the reward-fitting objective. By incorporating this optimism term, the method ensures that the resulting reward model explores out-of-distribution regions more effectively, leading to responses that are either globally optimal or potentially good in unexplored areas. This active exploration mechanism helps the language model to balance between exploring novel responses and exploiting previously observed ones, ultimately leading to a more accurate and aligned model.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method, Self-Exploring Language Models, SELM, works through an active exploration approach for online alignment of large language models, LLMs. The algorithm iteratively updates the LLM without a separate reward model by incorporating an optimism term in the reward-fitting objective. This optimism term encourages the LLM to explore novel and potentially high-reward regions by eliciting responses with high potential unknown to the reference policy. The algorithm optimizes a bi-level objective that includes minimizing the logistic regression loss and maximizing the expected reward while maintaining a small deviation from a base reference policy. By reparameterizing the reward function with policy parameters, the algorithm ensures that the LLM balances between exploring novel responses and exploiting previously observed ones. The algorithm actively generates out-of-distribution responses worth exploring and receives feedback to reduce uncertainty in these regions. The process is executed iteratively, with the offline preference dataset split into 3 portions for each iteration. The algorithm uses AI rankers to provide feedback on model-generated responses and original chosen or rejected responses. Through this guided exploration, SELM mitigates the indiscriminate favoring of unseen extrapolations and enhances exploration efficiency. The algorithm encourages the LLM to avoid generating low-reward responses and selectively prefers responses with high potential rewards, leading to a more accurate and aligned model.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the proposed method, Self-Exploring Language Models, SELM, lie in its ability to actively explore novel and potentially high-reward regions in the vast space of natural language. By incorporating an optimism term in the reward-fitting objective, SELM ensures that the resulting reward model elicits responses with high potential rewards, either globally optimal or potentially good in unexplored areas. This active exploration mechanism helps the language model to balance between exploring novel responses and exploiting previously observed ones, leading to a more accurate and aligned model. The method also mitigates the issue of indiscriminate favoring of unseen extrapolations, which can occur in passive exploration methods, by guiding the exploration towards more rewarding areas while still fitting the preference data. Practically, SELM enhances exploration efficiency by reducing the chance of generating responses with low implicit rewards, thus improving the model's alignment with human preferences. In experiments, SELM has shown significant performance improvements on instruction following chat benchmarks like AlpacaVal 2.0 and MT Bench, achieving higher win rates and scores compared to iterative DPO baselines. The method also demonstrates robustness and consistent performance improvements in each iteration, showcasing its effectiveness in actively exploring and aligning language models. Additionally, SELM can be integrated into various online alignment frameworks, with or without a separate reward model, making it a versatile and adaptable method for improving language model alignment.
How is the method validated or tested?
The method is validated and tested through experiments on various benchmarks, including Alpaca Val 2, 0 MT Bench, GSM 8K Heliswag ARC Challenge, Truthful QA EQ Bench, and OpenBook QA. The performance of the proposed self-exploring language models, SELM, is compared against Iterative Direct Preference Optimization, DPO, and base models like Zephyr 7B SFT and Llama 3-8B Instruct. The experiments show significant improvements in length-controlled win rates on Alpaca Val 2, 0 plus 16.24% and plus 11. 75% LC win rates and MT Bench, plus 2.31 and plus 0.32. SELM consistently outperforms iterative DPO on various benchmarks, demonstrating the effectiveness of the active exploration method. Pairwise comparisons between SELM and DPO show SELM's superiority even with the same amount of training data. Additionally, SELM is evaluated in zero-shot, few-shot, and few-shot chain-of-thought settings on multiple-choice QA benchmarks, showcasing its robustness and superior performance compared to other iterative post-training algorithms like SPIN and DNO. The experiments validate that SELM effectively balances exploration and exploitation, leading to a more accurate and aligned language model.
What results were achieved with this new method?
The proposed method, Self-Exploring Language Models, SELM, achieved significant results in improving the performance of large language models, LLMs, through active exploration in online alignment. Specifically, SELM demonstrated substantial boosts in performance on instruction following chat benchmarks Alpaca Val 2, 0 and MT Bench. For Alpaca Val 2, 0, SELM significantly enhanced Zephyr 7B SFT and Llama 3-8B Instruct models, with length-controlled LC win rate improvements of plus 16, 24%, and plus 11.75% respectively. Additionally, SELM showed improvements on the multi-turn MT Bench, with score improvements of plus 2, 31 and plus 0.32. The method self-explored and enhanced the model monotonically, consistently improving performance in each iteration. Furthermore, SELM outperformed the iterative DPO counterpart and achieved better results even when the latter was trained with twice the data. SELM also demonstrated strong performance on various academic benchmarks, including GSM 8K, Heliswag, ARC Challenge, Truthful QA, EQ Bench, and OpenBook QA, OBQA, outperforming other iterative post-training algorithms. The method effectively balanced between exploring novel responses and exploiting previously observed ones, leading to a more accurate and aligned model. Overall, SELM proved to be a robust and effective approach for improving LLM performance through active exploration and alignment with human preferences.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the proposed method, Self-Exploring Language Models, SELM, include the potential risk of becoming overly optimistic with a large value of the optimism coefficient alpha, leading to decreased effectiveness. Additionally, the method relies on proper tuning of hyperparameters, such as alpha, to achieve the best trade-off between exploration and exploitation. Another limitation is that the method may not be as effective when applied to weaker base models, as demonstrated by the performance improvements being more significant when using stronger base models like Llama 3-8B Instruct compared to Zephyr 7B SFT. Furthermore, the method requires careful dataset partitioning and update rules, which may introduce complexity and additional computational overhead. Additionally, the method's effectiveness heavily relies on the quality and diversity of the training data, which may be challenging to curate in practice. Lastly, the method's performance may degrade after the RLHF phase on some benchmarks, known as the alignment tax, which could limit its overall effectiveness in certain scenarios.